Good afternoon, everyone. Welcome to Containerization for the Hybrid Cloud. I want to talk to you a little bit about the containerization wave coming through the technology platform right now. I'm going to talk a little bit about the actual history of containers, kind of where they started, where they are today, what need they actually fill. We're going to look at Docker and Kubernetes as the two main technologies for our stuff today. We're going to move from there into actually looking at hybrid cloud architecture, kind of seeing how that would actually look if you're trying to do that and set it up. We're going to then talk a little bit about security concerns and what that's going to mean for your organization. There's a whole lot of questions with that because you're connecting the cloud to your on-premise and everything in between. And last, we're going to talk a little bit about a couple of tools for trying to make all this a little bit easier on you. So in the beginning, there were servers. And servers provided you all sorts of hardware and CPU and RAM and persistent disk, networking, and you could run your applications on that, and it was great. You could run all this stuff we'd never been able to do before. But the problem was you had all of your applications living within the same space. If you had one application that needed a certain library as a dependency and some other application needed a different version of that, you had to do weird things to try to make those fit together and not conflict with each other on the system. So people said, this is ridiculous. Why is this happening? Why are we having all of these conflicts? And they got together and said, there's got to be some way we can actually separate and isolate all of these things apart from each other. And then we got virtual machines. We had entire operating systems. We had all the libraries, everything all packaged up into one nice little container that said, look at this. We can run everything we want all together. No big deal. However, that's very heavy. We now had all of these operating systems we had to run all at the same time. And we had all these libraries that were just copies of copies of copies. It was very, very heavy on top of our already heavy architecture. So a bunch more people got together and said, hey, can we make this lighter? We've got all of these kind of shared dependencies for the kernel. We've got all these things that are doing essentially the same basic thing on the bottom. Can we just package and ignore the operating system? And that got us to containers. And my image didn't load. That's awesome. Live demos, man. Okay. 1 second, let me see if I can fix that. Maybe. Well, that's disappointing. Okay, so that should be a picture of containers. I don't know what happened. I don't know why the containers aren't there. Use your imagination. Playing in the theater of the mind. No matter how many times you practice this stuff, it never works out when you do the live demo. Okay, so pictures of containers. Actual shipping containers is what that should have been. What containers give us is unitized loads. Same thing for shipping containers. Instead of having to maneuver all of the individual cargo around on a ship, you have to pack it into a container, and then from there you can lift it onto a ship and haul it wherever you want to go. The other really nice thing about shipping containers, and kind of our analogy here as well for software containers, is that they can go on all of these different modes of transit. You have the same shipping container can be put onto an actual ship. You can put it onto a train. You can put it onto a truck, and it will get it to where it needs to go. And actually, kind of interesting fact too, shipping containers weren't invented until 1956. So before that, you had all sorts of weird standards of trying to put things on boats and trains and everything in between. The shipping container really revolutionized the modern shipping industry. Pretty cool. So here's kind of a big picture of how all of this looks. When we were on the servers, we had the apps, and we had all of this kind of wasted hardware space. You would have your, maybe a single server dedicated to your LDAP server. Maybe it's a single server dedicated to your email server. But you didn't put too much stuff on it because then it started conflicting, and that was just a hassle to maintain. But again, we were wasting all of this resource power. Moving up to virtual machines, well now look at this, we've got these more apps that we can actually run at the same time on our hardware there. That's great. We've got our base level OS here. Virtualization has a little bit of like layer by itself that it requires. Actually, there's also some interesting work with that. You can, instead of running the full OS, you can run hypervisors that just run virtual machines. There's other optimizations that were made in between here. But essentially, you're still running, again, another version of different OSs. Could even theoretically be the exact same OS. You never know. But you'd have a little bit better utilization of your total power now with actual code that you care about running. You're not buying hardware to run an operating system. You're buying hardware to run an application of some sort, to do some useful processing for you. Moving up to containers, we still have some wasted overhead with the actual containerization stuff. With the containers, how they actually communicate is a daemon process in between them and the OS. For our purposes, it's going to be the Docker daemon. But now you can see we've gotten a lot better utilization of our total hardware with more application stuff that we care about because of the lightweightness of a container. How containers work underneath. There are two main technologies that support containers: namespaces and cgroups. And they're features of the Linux kernel. And actually, when containers first started, it was specifically a Linux-only feature because that was the only way you could get these two specific features. Namespaces restrict what you can actually see inside your container, and cgroups restrict how much of that you can actually use. So with a namespace, you have, these are the big six here that actually make containers possible: PID, mount, net, user, UTS, and IPC. Each one of these is a separate hierarchy tree that lives in the host space, but it is a projection into the container space. And what that allows us to do for like the PID space specifically is restart our processes at PID 1, which our init system at PID 1. On the host system, it's obviously not running at PID 1 because the host system is running PID 1, but it is a translation layer in between that says PID 1 here actually means PID 1524 over here. Mount, likewise, gives us the ability to only show specific mount points into our containers. Net restricts our ability to use networking, what specific network accessories you can see. User is another thing, kind of like PID, where we're allowed to reset our user space so that root can be user ID 0, which is really, really important. The UTS space allows you to change host names independently between the host and the container. And IPC is inter-process communication, so you can use pipes and other stuff like that inside the containers without affecting the host. So all the stuff gets contained within its own namespace. The cgroups, what they do is they actually restrict. They put a limit, a hard limit on the amount that you're allowed to consume. If you didn't have cgroups and you just had namespaces, then you could use up to the entirety of the hardware that you had access to. With cgroups, you can say, here I can only use like 1 core out of my 10 cores or 12 cores, whatever that I have available. Memory, you can put strict memory limits, so you can't just consume everything. Block IO, not only can you restrict the amount of space, you can restrict like actual throughputs with that. And network also, you can restrict the total amount of networking you can push through. Apparently none of my images loaded. Fantastic. All right, so this picture should have been, again in our imaginations, a picture of containers being moved around. And this is what Docker allows us to do. We have portability in our unitized workloads, our containers, by the way Docker works. Fun fact, that whale that is the Docker's mascot is named Moby Doc. And fun facts. So why specifically Docker? Docker allows us to make containers as a configuration as code. It has a file called the Docker file, which actually sets up what the container has in it and what specific stuff it can do. Because of that, we can actually also implement security in our CI/CD pipeline. We can scan these configurations before anything gets pushed to a production level environment. Because also it's portable, we know that what is running in our dev environment is the same that is running in our test environment, that is the same as running in our QA environment, that is the same as running in our production environment. Scanning it once, we can be sure that it's the same configuration across all of them. The container registry is a very powerful feature as well. Think of it kind of like GitHub, except for your actual images for the containers. The really nice newer feature, is being able to sign your images, so you can be sure that you have exactly the image that you're getting. You can do hash sums, everything like that with on it. Application isolation and network isolation are both features generally of containers, but Docker allows that with a couple of extra overlay type layers, which are really nice. It just kind of makes the process of creating containers a lot smoother. You can actually just go and create containers on your own entirely. There's just using straight up Linux command line, you can just create containers. But that's a very long drawn out process of setting namespaces, creating like binaries into certain places. Docker made all of that a whole lot easier for us. Here's a kind of generic Docker file. It's their hello world. So you'll notice that every Docker file starts with a from keyword, and that allows us to build Docker files build Docker containers in layers. The from scratch means it's a no-op base layer. There's nothing that's being done. It's just zero. I'm starting from scratch. The Docker file copies then this, it's actually a binary, it's not shown here, but a binary called hello to the root of the container, /. And at the end, what we'll do is run this cmd command of hello at the root of the container. And if you actually just do docker run hello world, this is the output that you get. I did not have the hello world container on my local system. It's one that's up in Docker Hub. So when you start running Docker, it looks for the images to start with on your local machine. And if it doesn't find it, it says, hey, go to the registry and pull it for me. Other thing I forgot to mention, the registry, you don't have to use the public Docker Hub registry. It's great. It's really convenient. There's a lot of official images. There's a lot of like actual paid services you can use through that. But you're also more than welcome to host it private on your own servers in your own premise. That way you're not pushing and pulling from the internet if that is a concern for you. Additionally, if you're, again, we're talking about hybrid cloud, using any one of the major cloud providers, every one of them has a container registry that is scoped into your specific area. So that way you're not having to, again, push public, but you're still being able to take advantage of cloud resources. Okay, so yeah, went up. I am pulling this directly from Docker Hub because it's their public Docker environment. It checks the latest. Normally with each one of the containers, you have a tag for it. And if you don't specify a tag, it just pulls the tag latest by default. So it pulls this down and said, okay, we found it, hello world latest. And then it runs this command, which outputs hello from Docker. So that's a real simple one. Going up a little bit, there's a lot of ones that use in Docker Hub that are base images that you can build from. So if you have like a base operating system that you actually want to use, CentOS, if you want RHEL, if you want Ubuntu, Fedora, what have you, you can grab and start using from CentOS. But these also still have to be built as base layers. So from scratch, we add all of this stuff that is the CentOS 8 container. This is actually the latest, which is why it's the CentOS 8. However, if you notice between these two, the hello world Docker file uses the copy command, and the CentOS Docker file uses the add command. Add is copy on steroids. It has a bunch of additional features that it knows how to handle, and specifically because we're copying a compressed tar file into our root directory here, it says, oh, I know that I need to actually uncompress that onto that root system there. And that way also you don't have to keep the entire list of the operating system in version control. You put your tar files, your built files into that. The labels are useful but not that important for what we're going to talk about, so we're going to skip over that. But by default, this, when you run the CentOS, just like we could run hello world, you get a bash prompt. As you build the layers, you can override whatever that command is. So if you wanted to do something different, you just put another command. You can do from CentOS, and then literally the next thing you just be command. Hi, sure.
When you
By default, I believe you have root, yes. And you can restrict that. There's a whole lot of security configuration that you can say, I want to be using user space this. You can create users in the middle of these files, and there's a lot of them. Again, this is a fairly basic one, so you're just a straight up root user into CentOS. I actually want to show you Docker Hub's really nice for this. There's a huge amount of different tags, so you can get versions going back like pretty far. Latest by default here. And you can actually look at the tags. So some stuff's working today. Good. And you can actually see individual commands as it would be built on the layers. You can see that this specific add file, which is the giant CentOS tarxz, is adding 68 megabytes into our image. One of the other ones you can use that if you need just a very, very, very basic bare bones is Alpine. It's very, very lightweight. You can build off of that for very lightweight container images. Just some good practice stuff. Okay. Okay. Man, none of my images loaded. Okay, well, here we are. Okay, so Kubernetes is kind of another whole layer on top of Docker. What Kubernetes brings is automation for deployment, scaling, and management for our containerized, and remember, going back, unitized workloads. This picture with a much larger shipyard. Imagine in your head, all these containers spread as far as the eye could see. So what Kubernetes brings to the table for us, where Docker you had single applications at a time inside of your containers. You could put a couple of them in there at the same time. There's some stuff with that. But you're still looking at it at a single application chunk. But when you're deploying anything modern, you're not looking at it as a single tiny application chunk. You may have, here's your front end, here's your cache, here's your middle layer, here's your back end, here's microservices 1 through 10 off to the side doing other crazy stuff. All of these things are pieces that have to interact. And doing that with just strictly Docker is hard. So Kubernetes allows us to abstract up and configure the way that our containers end up on our hardware as code again. So we're having configuration for the containers as code and the configuration for our deployments in our environment as code. Not strictly infrastructure as code, which is an important kind of distinction between what Kubernetes does and does not do. Kubernetes manages your containers. It does not manage the underlying hardware that it runs on. Fun fact, so Kubernetes is actually a Google project, originally called Project 7 of 9. Google's whole container platform is called Borg, and when they were trying to figure out a better way to manage this, they created this Project 7 of 9 as a friendlier Borg. So the 7 spokes on the Kubernetes wheel are a reference to the reference to Project 7 of 9. Another interesting thing, you'll see Kubernetes frequently referred to as K8s, just to make it shorter because Kubernetes is a very long word. Also, other fun fact, Kubernetes is a Greek word meaning helmsman. You're navigating the waters. Okay, so going back to our diagram a little bit here again. Instead of having the container be our base unit inside of Docker, our base unit in Kubernetes is the pod. And what the pod does is allow us to group applications together. And this, still with a pod, you're supposed to have a single main application inside of your pod, but it allows you to have a bunch of helpers along with that pod. So again, a messaging service, some sort of queue, a cache, any kind of thing that makes your app run easier. If you have some sort of communication layer for talking in between specific apps, all of these things can be packaged into a pod. And when they get deployed, they are guaranteed to be run together and can then talk to each other. It's really cool. So stepping up again, Kubernetes is node aware. So each one of your individual pieces of hardware that can run Kubernetes is a node and has to have Kubernetes installed on it to be able to then accept work from Kubernetes. So it understands what the underlying hardware is, but it can't, again, manage what that underlying hardware is. So then Kubernetes will, there's actually a master and nodes, which I'll show here in just the next slide. But the important thing is the pods get scheduled onto nodes, and they consume some chunk of resources from that node, some amount of hardware, CPU, network, persistent storage, all these different things you can put together. The really nice thing also about Kubernetes is deployments. And what deployments do is allow you to create an availability for your application. So in this particular example, we've got 3 of our purple pod applications. We can call that our front end. We want to be able to constantly have a server available to serve traffic to our users. Really important. Accept connections in, serve traffic out. We have deployed 2 of our gold pods. Maybe that's some extra monitoring stuff we've got going on. We've got 1 of the green pods, and that may be our single analytics thing off to the side running, no big deal. If it completes sometime next week, whatever, it's just a thing that we're working on. And then we also have our 2 pods for our red application. So looking at how these are spread out, Kubernetes attempts to keep keep applications separated across the nodes so that it's highly available and balanced on the actual nodes themselves. You're not loading up node 1 with all of this stuff while node 2 and 3 are sitting idle. It tries, if there's 1 per node, 1 pod per node, to keep 1 of them active at all times on each one of the nodes. There's a bunch of other different configurations for this, but it's configured inside of a deployment file, which is YAML. Everybody loves YAML. YAML's fun times. But then as the nodes come up and down, we can see, let's say if we lost our node 2 here, it says, oh no, well, I'm supposed to have 2 of our red application, 2 of our gold application, and 3 of my purple application up. What do I do now? It will shift and bring back up the purple node on one of the other, or purple application on one of the other nodes. It may put, they'll probably put the gold application over here since there's not already a gold application on it, and then shift red over to here, and not really shift, it's more of a like respin up. So this node's gone, no big deal. But then, maybe next week that node comes back up, or maybe 5 minutes from now the node comes back up. It will again try to shift the workload to keep everything evenly distributed and available for us. Okay. All right. The really super powerful thing about Kubernetes is labels. They are key value pairs that are attached to every object across Kubernetes. That's your nodes, that's your deployments, that's your pods. Everything gets labels. It's really, really, really important. You can label these and then select on them later to do a bunch of fancy stuff. So let's say, we'll fast forward a little bit here, compliance. If you have part of your application that is handling PCI data, and you want part of your servers to be compliant to be able to use and process the PCI data, but you don't want to have to secure every single bit of your entire infrastructure against PCI stuff, you can tag your nodes with PCI, and then any of your Kubernetes pods that need PCI compliance can be pushed to the PCI compliant nodes. And you can do the same thing, HIPAA compliance, GDPR compliance. Another really useful case is blue-green releases. You can have pods that are at the same time. You can shift traffic between them. Any kind of dimension you can think of that makes sense for your application, label it. Labels are really, really cheap, and they're really, really, really powerful. Because they're also configured as part of the code, you can update them, which is also really nice. You don't have to know every single perfect label across your entire thing to start with. You can do your best guess right now, and then next week you get some crazy request, hey, put all of our stuff over in Europe. Well, how do we do that? Okay, well, let's go back and geotag all of our specific servers. Add the location, add regions, add whatever makes sense for your specific environment. The more dimensions you have, the more finely tuned you can mess with your applications and your nodes. Really, really, really important. So what should you label? Label everything. Go crazy with labels. They're really, really cheap. Label everything. Okay. So let's talk a little bit about hybrid cloud now. Okay. Really, the basic architecture for Kubernetes, you have a master node and 2 worker nodes. Technically, you don't really need all of these on separate hardware, and Kubernetes has a tool called Minikube, which allows you to basically spin all of these up inside of a single virtual container. So it's more of a testing bed that you can make sure your applications and configurations are working. If you have anything less than really a workload that needs 2 nodes, you're probably better off just doing Docker by itself. At that point, you're probably just in like toy application stuff. Kubernetes is a whole lot more configuration than you're going to need for some toy project. But again, very, very minimal basic architecture, a master and 2 nodes directly connected that can talk to each other. The second kind of end of that is highly available. You want at least 3 of the master nodes. If it ends up, if one of them crashes, it gets really weird if you only have 2. You lose your high availability to start with, and that's very bad. You want as many nodes as you can. At minimum 3, but you can go up from there. And what you'll do is connect the masters and the nodes in between load balancers. You still want to have the nodes communicating to a single endpoint, but the masters will have to be able to talk back out as well to the nodes. This is a very, very high-level architect design. There's a bunch of other layers of Kubernetes. It has an API server, which is also really important, and we'll talk a little bit about that here in just a couple minutes. That API server is really important, and it is how you connect to Kubernetes with your outside clients, your kube control, other stuff that you can do, dashboards. But specifically, you need the masters to be able to talk to the nodes, and they need to be able to bounce through a load balancer for highly available. So, nodes. Where can you put Kubernetes? Pretty much everywhere. Kubernetes runs on just about anything. If you got old Raspberry Pi sitting around, run Kubernetes on them. Anything higher than a Raspberry Pi 2, I think, right? Well, 2 or better will run Kubernetes. If you've got a bunch of desktop computers sitting around that are otherwise idle in the evening, put Kubernetes on them. Now you have a cluster to run applications on. If you got a giant data center, run it on bare metal. If you've got virtualized hardware, run it on your virtual machines. Kubernetes runs anywhere, well, except your kitchen sink, until it gets connected to Wi-Fi, and then it'll run on that too. In the cloud, you have a couple of different options. You're having essentially the same architectures, but you have 2 main camps for how you want to handle your cloud. You have infrastructure as a service or platform as a service. And a lot of that depends on how much control you want of how your containers run in the cloud. Excuse me. With a platform as a service, essentially, you're not worrying about the underlying hardware. You say, I have this application. I want you to go out and just run this cloud and keep it up, make sure it's available. If you get a bunch of traffic, scale it up. If you don't have a lot of traffic, scale it down. Do all that for me. I don't care. There's some fine-tuned knobs, and it varies between all the different cloud providers as to what control you get for those. But all the different ones have it. Amazon has Elastic Container Service, Azure has the Azure Container Service, and Google has App Engine. Those will run containers in different ways in different versions. The other side of that is infrastructure as a code, or infrastructure as a service, and that allows you to deploy your code onto basically just bare compute instances. That gives you a massive amount of control. And if you want that, if you need that, that's an available option. But you are directly installing Kubernetes onto every node. You're directly managing every node, keeping it patched. All of these other standard SA-type tasks are your responsibility. Here's a kind of basic idea of a very, very, very basic hybrid cloud architecture. You don't necessarily have to jump directly all in on the cloud. There are certain things that make sense to run in the cloud and certain things that make sense to run on-prem. If you're having a very, very sensitive workload, keep all of that data that is sensitive on-prem. But if you've got a bunch of analytics work that isn't really sensitive for any reason, maybe you've got just your website traffic logs and you want to analyze those over your past 6 years of data. Well, do you really want to use that on your expensive secured cluster here, or do you want to just push off to the cloud and say, hey, spin up resources, get it done whenever it gets done, no big deal. Do it cheap at the cloud. They still need to have data that can talk between each other, but they're not strictly one giant Kubernetes cluster at that point. The VPN allows traffic to go between them, and specifically the data. So push data that you don't care about to the cloud, or if you do have less sensitive data, you can also do that in the cloud. It very much depends on what your specific security posture is and what kind of data you're looking for. And again, also the compliance for HIPAA, GDPR, PCI, any of the other dozen standards that matter for that. Here's a more advanced one, and we're going to kind of talk about this one for a few minutes. The way to do some advanced stuff is essentially making one giant Kubernetes cluster between everything. And this is where it requires a bunch of fancy networking. Essentially what you'll need is DNS on local and cloud. And your primary route should be to a load balancer, and you can host that either in the cloud, on-prem, doesn't really matter where that's hosted. The primary DNS should point to that load balancer. But if that one happens to go down, DNS should have a failover back to a second load balancer for either the on-prem work or the cloud. And that way, you're not losing both sides of your cluster if one of them goes down, or if you happen to just lose connectivity between them for some catastrophic reason. The big thing here is that the masters are all in one control plane. You can do that using the kubeadmin command, kubeadm. You join all of them together, and that will work because we have still a VPN inside of this. The DNS pointing to this load balancer will have the traffic balanced between on-prem and cloud, and that way it gives control across everything, which is pretty big. Very big picture. There's, again, more stuff. Make sure you have firewalls set in place. Very, very high-level architecture. There's more to it than that, but that's the general idea for how you pull this off. This was a fantastic Dilbert comic strip. Was. So, Dilbert's complaining to his boss that, he was not allowed to make his applications actually cloud native. And the boss is like, wait a minute, I'm not allowed to just say, Kubernetes to make everything work? And Dilbert's just visibly disappointed. Why? All right, security concerns. Now, probably what you've actually come here to HackerCon for. Each one of these different pieces we're going to talk about has different concerns around it, and a lot of it is questions that you pretty much have to answer for yourself. I don't have any silver bullets, and this actually is, again, a very complicated architecture, so it very, very heavily depends on exactly how you decide to implement it. A couple of basic concerns, though, with Docker, container breakouts. You have all of these things scoped pretty well, but it's not perfect. Occasionally, stuff gets out of the containers, and then it gets onto the main host, and then it can do whatever it wants. It's very rare, it's very hard, but it has happened. Docker, like pretty much everything else, has CVEs against it. The other thing you have to worry about is kernel exploits. The kernel being shared across all of the containers, if there's some sort of malicious exploit with that, getting access out of one container gives you access to do stuff in other containers that you may not have even known were sitting right beside you. Malicious images. You can mitigate this a little bit with your trusted images and signed images and stuff like that. But it's a very valid concern if someone ends up getting a key and uploading something that otherwise would be very bad for you. Make sure you know what you're running in your environment. Very, very, very important. Denial of service. This is kind of a half security and half not security kind of thing. If you fail to configure the images properly, they don't get the C group stuff applied. And then they can just consume whatever resources they want. So if you don't have the resource limits, you might end up having a container that spins out of control. It might start just consuming truly ridiculous quantities of your memory. And then, oh, well, now I'm out of memory, and everything starts crashing around you. It's very bad. Again, it may be entirely unintentional. It may be entirely intentional. That's kind of where your malicious images versus your other configuration scanning has to happen. Another thing to worry about within Docker containers is unnecessary package binaries. Do you really need to have a full package manager inside your container image? Do you need apt? Do you need yum? Why put it in the container? That's just one more vector that you have to worry about. Same thing like curl, wget, these things that you can go and pull things from the internet. If you don't need that, don't put it in there. On top of that, from the security point, it also makes your images lighter, which makes them more efficient. We can run more stuff on the same amount of hardware. It's good. Kubernetes. A couple of important things with Kubernetes. I mentioned earlier that there's the API access. Tesla actually had this problem last year. They didn't secure their API servers for Kubernetes, and people found it on the internet and then submitted a bunch of, I think it was Bitcoin mining pods into Tesla's main cluster. And, well, that was bad. They found it and fixed it, but securing your API access, very, very important. So again, we have pods instead of containers, but the containers can, if we have other exploits, get privilege escalation. There's a set of containers that Kubernetes uses that kind of does all of the internetworking for its piece of this, all the monitoring, all the other stuff, and those run within a privileged space in Kubernetes. You don't want your other containers to also be living in that privileged space. And there's ways to mitigate that, but container privilege escalation is one of the concerns for Kubernetes in general. Overly permissive network settings. If you have things open to the internet, then you never know what's going to happen. You might end up with a bunch of blockchain or Bitcoin miners on your Kubernetes cluster. Bad times. Lastly, and this is kind of a just general everything, are you scanning your environment? How are you scanning all of your pods? How are you scanning all of your clusters? What interesting stuff is out there, and what are they doing? Do you know where your pods are tonight? Okay. So the network. With hybrid cloud, generally you're going across the public internet. The way to mitigate that, obviously, VPNs, but one question you can ask is, can you feasibly co-locate with your cloud's edge? A lot of the clouds have services that you can basically plug directly into their network and skip the public internet entirely. It becomes encrypted to them, and at your point, literally in the data center beside each other. It's expensive generally, but can you do it? Is that actually something that you're willing to pay for to mitigate something the VPN can't otherwise handle? VPNs for every single one of the cloud providers have bandwidth caps. So will having a VPN actually offer you enough bandwidth between on-premise and cloud to satisfy what you're going to be doing between them? Maybe. And what happens if one side or the other goes down? Is the stuff running in the cloud really important? Is the stuff running on-premise really important? Can you switch over? Can you fail over one way or the other? Entirely depends on how you design stuff and what actually is important to you. Again, is it your analytics load that's just kind of running queries in the background, generating random reports? Yeah, whatever. Is it your main website generating you millions of dollars? They might want to take a look at that. Data. Where does your data live? So another big concern with hybrid cloud is putting data in between two of them. And sometimes if you're truly going hybrid where you're spinning up things back and forth, is your data actually syncing across properly? Are you making sure that you're working on the most recent copy, the best version of your data? And then how do you verify that? It's a big question. There's not really a good single answer. Does your cloud offer secure enough storage? I specifically emphasize enough there because every one of the clouds offers some kind of security, but does it offer the security that you need for your space? Is it going to allow you to put classified data on there? Well, most of them don't allow you to do that unless you're in like the GovCloud kind of space. Do Do you have specific geolocation requirements for your data? Again, GDPR, something like that. You can't put data from over there over to here. It's really important to keep everything separate. And last, secrets. So with all of this, we're spinning containers up and down. We're going to need access to the API keys, SSH keys, all these other secrets, database passwords. How are they being stored inside of your environment? Kubernetes actually has stuff for that, which is really cool. You can create Kubernetes secrets, and they just live inside the cluster. But is that what you're using, or are you using some sort of third-party like key store idea? How is it being stored? Especially too with being partly on-premise, partly in the cloud, how quickly can you actually mitigate a loss of a secret? If it goes, like if you find out that it's been compromised, how quickly can you shut it down and get a new one out and deploy it in your environment? Do you want to have your website down for a day? Probably not. And more importantly than that, and kind of feeding back to that, do you have a plan or a system for rotating your secrets? That will definitely help in the event that you end up losing one. All right, last. Talk a little bit about tools. So Docker. That's pretty much it. Docker is how you run pretty much everything through Docker. Kubernetes has two that you'll specifically want to know about for hybrid cloud. Kube Control, which you'll hear people pronounce all sorts of different ways. It's your main API access into deploying pods, to applying deployments, to doing all of the things with Kubernetes that you need to do. Kube Admin will allow you to actually create the bare clusters to start with. Orchestration. So if you're not 100% convinced on Kubernetes, there are other options. Docker Swarm is the official Docker version of Kubernetes. It's the same kind of availability and everything, bringing it up and down, making sure that there are enough running, putting them on nodes, keeping things load balanced. It exists, but Kubernetes seems to be the preferred way of doing it. There's Mesos and also DCOS, which is a enterprise version of Mesos. A company called D2IQ puts it out, and there's actually images for it in Azure by default. I think a couple of the others are getting to that. And also, if you want to just use a container platform, OpenShift, Red Hat has that now. And lastly, talk a little bit about the security. Docker EE has a bunch of really important stuff. One thing in particular is security scan. It will actually show you layer by layer what specific CVE vulnerabilities exist inside of your containers. Super nice. Istio is a giant traffic policy engine. One really cool thing about it, Google is using it with Kubernetes and their Google Kubernetes engine to build hybrid clouds in a box. It has a common control plane with Kubernetes. It's their Anthos product. It's expensive, but it allows you to just plug it in and go. You get Google Kubernetes engine on-prem, you get Google Kubernetes engine in the cloud, one thing to rule them all. High Trust. This is another one that I was working with a little bit over the summer with contracting. They have mostly VM space. So if you're not 100% sold into containers at this point, High Trust is a good place to start because they also have a container piece. So as you're migrating from VMs to containers, you have a common tool moving you forward. And StackRox is the one that I really, really want to show you. Actually, been working with them on and off, again, with the consulting stuff this summer. And I told them I was coming, and they actually gave me an environment to play with, which is pretty cool. I also have swag, pens, and stickers, and stuff like that if you guys want to come up and grab stuff. They have a very nice interface for essentially profiling your entire cluster. And more importantly, they have what I think is their really big feature, this risk tab that actually prioritizes all of the running stuff on your environment. They've got this dashboard here that says, okay, you got 98 violations. But if you go and submit that as a ticket, all right, 98 violations, you're just going to get laughed at. There's no way to prioritize that. It'll get done when it gets done, whatever. But with the priority ranking that they offer, you can actually see this is why we're doing this. There's weird run conditions. There's different pieces that are old. There are pieces that have high profile CVEs that are easily fixable. So, maybe submit the top 5 to your developers and say, hey, go fix these. They're really important. So start adding stuff to the backlog. Alrighty. Okay, so that's the majority, the very, very high level majority for how hybrid clouds work. If you have any questions, I'll be around all weekend. Come hit me up, come talk to me. I love talking about cool stuff. If you're interested in more of the deep dives, shameless plug, go to linuxacademy.com. They've got stuff for Docker, containers, Kubernetes, any of the clouds you want to learn. Very cool platform. Yeah, thanks a lot.